I want to find out where my linear systems intersect, but I don't want to graph it. I don't want to just use the calculator. Because a lot of times when you use a calculator, one of the things you're going to find is that when you have an intersection, it's not going to be a rational number. It might not be an integer, it might not be a rational number, it'll be some irrational number. So when you're doing it on the calculator, you're estimating. But when you're doing it with algebra, you can get an exact number. Like you can get radical 2 for an answer. Whereas if you do it on the calculator, it's giving you 1.416, blah, 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 and you're not really getting an exact answer. So doing it algebraically is really nice, and there's two ways to do it algebraically. One is the substitution method. So it tells you here what I'm going to do is I'm going to solve for one of the variables in one of my equations, and then I'm going to take that and I'm going to plug it into the other equation. And this is a nice way of writing it, but it's much better to look at an example. So let's look at an example. These are my two linear equations. So this is my linear system. 2x plus 5y equals negative 5. And the other one is x plus 3y equals 3. So those are the two equations that I have for my linear system. And the way that I like to set it up, which helps me stay on track, is I like to set it up in two columns. When I'm doing the substitution method in particular, I like to set it up in two columns. So one of my equations is over here, and my other equation is over here. The substitution method works the best when I have one variable that has a coefficient of 1. If all of them have coefficients greater than 1 or less than 1, but not 1, it's easier to use another system, which we're going to talk about in a minute. But when one of them is equal to 1, it makes it really easy to use the substitution method. Because what I'm going to do here is I'm going to say, okay, well, I have x plus 3y equals 3. So it's really quick for me to just subtract 3y from both sides of this equation. And I know that x is equal to negative 3y plus 3. Oh, that's nice. X is equal to negative 3y plus 3. I'll just come right over here to my other equation. And instead of writing x, I'll write negative 3y plus 3. Because now I have an equation that only has one variable, and I can find an answer to it. You always have to have the same number of equations as you do variables in order to solve it, in order to solve a system. So if I was just given this one equation here, that 2x plus 5y equals negative 5, and somebody says solve it, what are you talking about? You only gave me one equation, you can't do it. But since they gave us this other equation, I can now put my x in terms of y, and now all I have over here are y's. So here's the algebra, right? I mean, I go, I distribute my 2 to the negative 3y plus 3, like that, see, so that you can see it on the video. And I have negative 6y plus 6 plus 5y equals negative 5. I get negative y plus 6 is equal to negative 5. Negative y is equal to negative 11. So y is equal to 11. Well, that's kind of nifty. Now that I know that y is equal to 11, I can just kind of come right back here to my other side and plug my y is equal to 11 into that equation. So I have negative 3 times 11. X is equal to negative 3 times 11 plus 3. So x is equal to negative 33 plus 3. X is equal to negative 30. So the solution to my linear system is the ordered pair 30, negative 30, 11. Does that make sense? Any questions on that? I like the substitution method. You know, it makes sense to me. The elimination method, which we're going to do in another minute, doesn't make as much sense, but it also comes in handier in more situations. Once you get your solution, what do you need to do, other than party?
Check it.
Check it. You need to check your solution. And you need to check your solution in both equations. Go back up to your original equations and check your solution in both equations. If it doesn't work in both equations, you made a mistake. If it works in both equations, good. Any questions on substitution method?
We're good with substitution then.
All right, then let's do this. Let's